A football-sized rock just crashed through a Houston rooftop. A 7-ton asteroid exploded above Ohio with the force of 250 tons of dynamite. And a daytime bolide over Europe was watched by more than 3,000 people in a single morning. This year, the sky over America is doing something it has never done before, and the scientists tracking it are quietly alarmed. You will see the rooftop the rock went through, the cornfield where hunters found a black stone, and the chart that puts this year nearly 4 standard deviations above every year on record. If space mysteries pull you in, hit subscribe and stay close. Stay with me. The numbers get stranger from here. The number that broke the meeting was 3.9. In late March of this year, a researcher named Mike Hankey sat down at the American Meteor Society and pulled 15 years of fireball data into a single spreadsheet. He filtered by witness count. He filtered by sonic boom. He filtered by event size. And every filter he tried pointed at the same impossible spike sitting in the first 3 months of 2026. The Society has been logging fireball reports since 1911. Their digital platform has been running smoothly since 2018. They know what a normal year looks like. A normal first quarter brings about 20 events with 50 or more witnesses. 2026 brought 40. A normal first quarter brings 8 events with 100+ witnesses. 2026 brought 16. Every category doubled. Every threshold smashed. When you stack that pattern against the historical curve, the number that comes out is 3.9 standard deviations above the mean. Translated into plain odds, that is roughly 1 chance in 21,000 of this happening by accident. Now, scientists are usually careful people. They hedge, they qualify, they use words like preliminary and warrants investigation. But the Society's published report did something unusual this spring. It said the signal was real. It said the rocks themselves had gotten bigger, not just the cameras pointed at them. And it said nobody could yet explain what had changed. Picture a sleepy weather station that has measured the same gentle rainfall every March for 2 decades. Then one March, the rain falls so hard it floods the basement. You would not blame the rain gauge. You would look up at the sky and ask what is different about the clouds this year. That is exactly what the Society did. They looked up, and what they found is that something in the river of small rocks flowing past Earth has shifted. The flow has gotten thicker, the pieces have gotten heavier, and nobody can yet point to the source. A team of independent analysts pulled the same numbers from a separate archive called CNEOS, run by NASA's Jet Propulsion Laboratory. They came to the same conclusion. 2026 is not behaving like a normal year. Whatever is happening, it is happening across 2 independent datasets, 2 continents, and multiple instrument types. Bill Cook, the man who runs NASA's Meteoroid Environment Office, has long admitted that even the normal seasonal climb in spring fireballs happens, in his own words, for reasons science does not fully understand. That admission was on the record long before this year began, but the spike that arrived in 2026 sits far above even that mysterious baseline. Here is what makes the pattern truly strange. If the small rocks were unchanged but more people had cameras, the small category would have grown along with the big category. It did not. The smallest fireballs are right where they have always been year after year. Only the big ones jumped. That single detail rules out almost every easy explanation. So if it is not better cameras, and it is not social media, and it is not a known meteor shower, what is it? That question is what sent meteorite hunters racing across Ohio cornfields the very next week. Sherry James was home in North Houston on the afternoon of March 21st, when the sky cracked open. She heard a sound like a thunderclap, but the day was clear. She heard a low boom that rolled across the suburbs and shook the windows of her house. Then she heard a second noise. This one came from inside her home. It came from the ceiling above her. She walked toward the sound. Plaster dust drifted down through a beam of afternoon light. And there, sitting in the middle of her floor, was a rock the size of a football. It was black. It was pitted. It was warm to the touch. It had just punched a clean hole through her roof and dropped onto the boards of her living room, as if delivered by some impossibly precise mail service from outer space. She did not touch it with her bare hands. Somebody had warned her once that meteorites should be handled with gloves, that human skin oils can ruin their value to science. So she picked it up with a towel and set it gently on her kitchen counter. The local fire department arrived within the hour. Captain Tyler Ellingham of the Ponderosa Fire Department looked the stone over and shook his head. There was no construction nearby. There were no trees overhead. There was no plausible way for a football-sized rock to fall through a Houston roof on a clear Saturday afternoon. The fire team called it what it obviously was, a piece of an asteroid. The math of that afternoon is worth pausing on. The original rock was roughly 3 feet across and weighed about 1 ton when it entered the atmosphere. It came in fast and hot and exploded in a fireball roughly 29 miles above the Houston metro area. The energy released was equivalent to 26 tons of dynamite going off in the upper sky. That is the boom Sherry heard. That is what rattled the windows from one end of the metro to the other. The fireball itself lasted somewhere between 1.5 and 7.5 seconds, depending on which witness you ask. The society logged more than 100 reports from across Texas and into Louisiana. Dashcam footage caught the streak from a highway just outside the city. People described a brilliant flash, then a sound like a jet engine breaking apart, then silence. Only one fragment made it through the roof. Most of the original rock vaporized in the airburst, scattering microscopic dust through the stratosphere. The piece that survived was small enough to slip through the heat unharmed, and heavy enough to keep falling all the way down to a Texas living room. If you are wondering what the odds are of a meteorite hitting a specific house on a specific afternoon, the honest answer is that nobody knows for sure. The last confirmed indoor strike in the United States before this one happened, years ago. The chance of being inside one of these events in any given lifetime is so small that insurance companies have never bothered to write a policy line for it. And yet here it was, sitting on a kitchen counter in Texas, a piece of something far older than Earth itself, delivered through a ceiling on an afternoon that should have been ordinary. Houston was the third strike in 9 days. The second one was about to send 100 meteorite hunters running into the cornfields of Ohio. 4 days before Houston, the sky did something even louder. At 8:57 in the morning on March 17th, a small asteroid roughly 6 feet across and weighing 7 tons slammed into the upper atmosphere directly above Lake Erie. It was traveling 40,000 miles per hour. The sun was already up. People were driving to work. School buses were rolling down country roads in Olmsted Falls and Medina, Ohio, when the air above them turned into a furnace. A bus garage camera caught the whole thing. The video shows a clear blue Tuesday morning, the kind of late winter sky that promises a normal day, and then a brilliant streak of white-hot light cuts diagonally across the frame. The light is brighter than the morning sun behind it. For about 4 seconds, the camera struggles to expose properly. Then the streak vanishes, and the recording catches what comes next. 3 minutes later, the sonic boom arrived. It hit Cleveland first, then Akron, then Canton. Windows rattled across a 100-mile arc. People reported the sound as a deep, rolling thunder that did not fade like normal thunder fades. It rumbled, it carried, and then it stopped, leaving a strange silence behind it. NASA's tracking team got the trajectory pinned down within hours. The rock had entered the air over Lake Erie, traveled 34 miles through the upper atmosphere on a southeasterly heading, and fragmented 30 miles above a small Ohio town called Valley City. The energy released by that fragmentation was equivalent to 250 tons of dynamite. To make that number real, picture this. 250 tons of dynamite is roughly 10 times the explosive force of the largest bomb dropped in a typical wartime air raid. It is enough energy to flatten a city block if it were released at ground level. But this rock did its work 30 miles up, where the pressure wave had room to spread and weaken before it touched anyone's window. That is the only reason nobody got hurt. The American Meteor Society received more than 220 reports from 16 states and Ontario, Canada. People in Pittsburgh saw it. A driver near Lake Erie said the light was bright enough to throw shadows on the road in front of him at 9 in the morning. NASA's Geostationary Lightning Mapper, a satellite instrument designed to spot thunderstorms from orbit, picked up the fireball as a clean flash of light against the cloudless ground below. What made this event extraordinary was the time of day. Almost every fireball you have ever heard about happened at night. The reason is simple. A streak of glowing rock against a black sky is easy to see. A streak of glowing rock against a sunlit sky has to outshine the sun itself before anyone notices. The Ohio bolide did exactly that. It was a daytime fireball bright enough to compete with the morning sky and win. These are rare. The Society logs roughly 1 or 2 confirmed daytime bolides over the United States in a typical year. This year, the first quarter alone produced several. Ohio was one. Europe had its own daytime fireball on March 8th, watched by more than 3,000 people across 5 countries. And in the hours after the Ohio sky went quiet, the hunt began. Somewhere in the cornfields between Medina and Akron, pieces of an ancient asteroid were waiting to be found. Before we go any further, you need to understand what these things actually are, because the word fireball gets used loosely and the science behind it is stranger than most people realize. A fireball is not just a bright meteor, it is a specific category defined by the American Meteor Society as a meteor that flares as bright as the planet Venus in the night sky, or brighter. That is the official threshold. If a streak of light hits that brightness level, it gets the name. If it does not, it stays a regular meteor. To make that brightness real, imagine standing in a dark field on a moonless night. The brightest object you would see, apart from a few planets, would be Venus low on the horizon. It would be sharp enough to throw a faint shadow on a white wall. A fireball matches or beats that brightness, but it does it while moving across the sky in 3 or 4 seconds. Some fireballs get bright enough to read a newspaper by. The truly extreme ones, called bolides, can turn midnight into noon for a heartbeat. What is actually burning up there is almost never on fire in the chemical sense. There is no flame. There is no combustion the way a campfire combusts. What you are seeing is a process called atmospheric heating. When a rock slams into the upper air at tens of thousands of miles per hour, it compresses the air molecules in front of it faster than they can move out of the way. That compression heats the air to thousands of degrees. The rock itself heats up too, fast enough that its outer layer melts and vaporizes. The glowing trail you see in the sky is mostly that vaporized rock and the superheated air around it, both of them shining like the surface of a small star. The speeds involved are difficult to picture. A typical fireball enters the atmosphere somewhere between 25,000 and 160,000 miles per hour. The Ohio rock was moving at 40,000. The Japanese fireball last August was clocked near 47,000. For comparison, the fastest rifle bullet ever fired travels at about 2,700 miles per hour. A fireball is moving roughly 15 times faster than a bullet and weighs anywhere from a few pounds to several tons. Most of these rocks come from one of 2 places. The first is the asteroid belt between Mars and Jupiter, where chunks get nudged loose by gravity and sent inward on long, slow orbits toward the Sun. The second is the trailing dust streams of old comets, which Earth plows through at certain times of year and which produce the regular meteor showers you may have watched on summer nights. Here is the critical part. A typical meteor shower particle is the size of a grain of sand. The streak it produces lasts a fraction of a second. The rocks behind the 2026 surge are millions of times larger. The Ohio bolide weighed 7 tons. The Houston rock weighed 1 ton. These are not dust, these are boulders. When a boulder hits the atmosphere, the energy released is enormous. The rock either survives the heat and reaches the ground as a meteorite, or it explodes in mid-air as an airburst, scattering tiny fragments and sending a pressure wave outward in every direction. Both happened in March, and one of them happened directly above a major American city. Here is where the story gets harder to dismiss as a coincidence. When the American Meteor Society first noticed something strange in the early March numbers, the obvious explanation was the boring one: more people own cameras now than in 2011. More people post videos online. More people know how to file a fireball report. Of course, the counts would go up. The sky was not changing, the audience was. Mike Hankey and his team had heard that argument before. They had heard it every time someone questioned a fireball spike, so they did something clever. They broke the data down by witness threshold and looked at each layer separately. Think of it like a building with floors. The ground floor is small fireballs with 10 to 24 eyewitness reports. The second floor is medium fireballs with 25 or more reports. The third floor is large fireballs with 50 plus. The penthouse is the giants, with 100 reports or more. If the surge were really just a reporting artifact, every floor of the building would have grown together. More cameras would mean more eyes on every fireball, big or small. The ground floor would have swelled along with the penthouse. It did not. The ground floor stayed exactly where it has always been. Small fireballs in early 2026 totaled 21 events, which is identical to the average for every prior year going back 15 years. The reporting platform was not adding eyes. It was not inflating counts. It was behaving normally at the bottom of the scale. But the second floor jumped 63%, the third floor doubled, and the penthouse, the giants with 100 plus witnesses, came in at 16 events versus an average of 8, exactly twice the historical norm. That pattern is the signature of physically larger rocks hitting the atmosphere. Big rocks produce brighter fireballs. Brighter fireballs are seen by more people across more states. A truly enormous event might draw 200 reports from a dozen states because it lit up the sky from coast to coast. A small one draws 15 reports from one county because only the people who happened to glance up at the right moment saw anything. So when the giant category doubles while the small category stays flat, you can rule out the easy explanations. The cameras did not change. The audience did not change. What changed was the rocks themselves. This is what statisticians call a hallmark signal. It is the kind of pattern that only emerges when the underlying physics has shifted, and it is the reason the Society used the phrase "warrants serious investigation" in their published report, which is about as alarmed as a professional meteor organization ever gets in public. The single month of March 2026 produced 5 events with more than 200 eyewitness reports each. That is more than every prior March combined since the Society began keeping digital records in 2011. 1 month, 15 years of history, and the math comes out lopsided. When a pattern survives every attempt to explain it away, scientists call that a real signal. The fireball surge is a real signal. The question is not whether something has changed. The question is what. And the answer to that question may be hiding inside a chunk of black rock pulled out of an Ohio cornfield 3 days after the Lake Erie bolide. The whole strange spring began with a single boom at the Canadian border. It was the 3rd of March, early evening, when the first major event of the 2026 surge slammed into the atmosphere above Vancouver. The rock entered the air over British Columbia and crossed the international border into Washington state within seconds, traveling fast enough that the sound of its passage lagged far behind the light. People in Vancouver saw it first. People in Bellingham, Washington heard it. The fireball broke the sound barrier as it descended, and that single fact is the key to understanding why this particular event mattered. Most fireballs burn up so high in the atmosphere that any sonic boom they produce dissipates before it reaches the ground. To produce a boom that rattles windows at ground level, a rock has to push deep into the lower atmosphere, where the air is thick enough to carry the shockwave intact. That means a bigger rock, a slower entry angle, or both. The Vancouver event did exactly that. Witnesses on both sides of the border reported a deep rolling boom that lasted several seconds and shook houses across the lower mainland and the northwestern corner of Washington. Some described it as a sound like a distant explosion. Others said it sounded like a heavy truck driving over a metal bridge. A few people thought a transformer had blown nearby. Then they checked outside and found their neighbors all standing in their yards looking up at the sky. The American Meteor Society logged a flood of reports within minutes. Cross-border events are unusual in their database, partly because the Canadian and American reporting systems do not always sync cleanly. But the Vancouver fireball was bright enough and loud enough that reports poured in from both directions. 5 days later, the European sky lit up. On March 8th, a slow-burning daytime bolide tracked across the skies of France, Germany, Switzerland, Belgium, and the Netherlands. The duration of that event averaged 5.5 seconds, which is exceptional. Most fireballs last less than 3. A 5.5-second daytime fireball is the kind of event that gets etched into the memory of everyone who happens to look up. More than 3,200 people filed reports on that single bolide. That number alone is roughly equal to a typical month of fireball reports for the entire European continent. The skies over 5 countries. One morning, 3,000 pairs of eyes pointed up. 3 days after that, on March 11th, a major fireball crossed France and Spain. 236 reports. The Society later marked this date as the start of what they called a sustained 13-day wave of large events. Pause and think about what that phrase actually means. A sustained 13-day wave. In normal years, the gap between large fireball events is measured in weeks. The atmosphere clears out, the skies go quiet. Then, another rock arrives. In March 2026, the gap collapsed. Large events were arriving every 2 or 3 days, sometimes on the same day, sometimes from completely different directions in the sky. The Vancouver boom on March 3rd was the first wave. The European bolide on March 8th was the second. The France and Spain event on March 11th was the third. Ohio on the 17th was the fourth. Houston on the 21st was the fifth. California, twice on March 23rd, was the 6th and 7th. 7 major events in 3 weeks, across 2 continents, with no known meteor shower active to explain any of them. The river of rocks had thickened, and nobody knew where the new flow was coming from. The March 8th European fireball deserves its own chapter, because nothing like it has happened on that continent in recent memory. The morning was clear across Western Europe. People were on their way to work in Paris, walking dogs in Brussels, sipping coffee in cafes in Cologne. The sun had been up for about an hour, casting that thin golden light that comes just after sunrise in early spring. Then, at roughly 9 in the morning local time, a second sun appeared in the sky. It was a small asteroid entering the atmosphere on a long, shallow trajectory. The shallow angle is what made this event extraordinary. Most fireballs come in steep, blazing for a second or 2 before they fragment or burn out. This one skimmed the upper air for 5.5 seconds, holding its brightness across an enormous arc of the sky. People had time to point. They had time to call their family members outside. They had time to pull out their phones and start recording. Then the fireball flared one more time and broke apart. The visual stretched across 5 countries. France saw it, Germany saw it, Switzerland, Belgium, and the Netherlands all saw it. The Society's reporting platform received 3,229 separate eyewitness submissions within 48 hours. That is the largest single-event report count in the platform's history. A few weeks later, hunters working a field outside a German farming village pulled the first piece of the rock out of the soil. It was small. It was dark. It had a glassy black crust on its outer surface where the heat of entry had melted and resealed the stone. And when the geologists got it under a microscope, they realized what they were looking at. It was a diogenite. That word probably means nothing to you, and that is fine. The simple version is that diogenites belong to a rare class of meteorites called HED, which stands for howardite, eucrite, and diogenite. These three rock types share a common origin. They were blasted off the surface of a single asteroid billions of years ago, and they have been wandering the inner solar system ever since. The asteroid they came from has a name. It is called Vesta. It is the second largest body in the asteroid belt, 400 miles across, with a massive crater on its southern hemisphere that scientists believe was carved out by a giant ancient impact. The HED meteorites are the splinters of that impact, scattered across the inner solar system over the eons. To find a diogenite is rare. The HED family makes up only about 6% of all recorded meteorite falls. To find one freshly fallen, with its glassy crust still intact, is rarer still. There are perhaps 2 or 3 confirmed HED falls in any given decade. In 9 days, the spring of 2026 produced 2 of them. The first was the German diogenite from March 8th. The second was about to be pulled out of an Ohio cornfield on March 18th. 2 rare meteorites, 2 continents, 9 days apart. And here is where the math turns truly strange. The 2 events arrived in the sky from directions 98 degrees apart, which means they did not come from the same orbital stream. They were not pieces of the same fragmenting rock. They were 2 independent Vesta family rocks, arriving from opposite sides of the inner solar system in the same week. The Society called that coincidence statistically remarkable. They were being polite. The honest word would have been impossible. Unless something has stirred the Vesta family. To understand why 2 HED meteorites in 9 days set off alarms, you need to know a little about Vesta itself. Picture a roughly spherical rock about 330 miles across, big enough that its own gravity has pulled it into a nearly round shape. It sits in the middle of the asteroid belt between Mars and Jupiter, alongside millions of smaller rocks. NASA sent a spacecraft called Dawn to orbit Vesta back in 2011, and the photos that came back changed how scientists understood the early solar system. The most striking feature in those photos was a crater near Vesta's south pole. It is enormous. It covers most of the southern hemisphere, and it is so deep that it punches almost all the way through the asteroid's outer crust. The impact that carved it out happened about 1 billion years ago, and it ejected an estimated 1% of Vesta's total mass into space. That ejected material became a debris field drifting outward in long, slow orbits. Some of that debris stayed in the asteroid belt and formed what astronomers now call the Vesta family. Tens of thousands of smaller rocks, all of them with chemical fingerprints that match Vesta's own crust. Other pieces drifted inward over millions of years, pulled by the gravity of Mars and Jupiter into Earth-crossing orbits. Those are the rocks that occasionally fall on us. Every HED meteorite ever recovered is, in some sense, a piece of Vesta. Now consider the math of recovery. There have been roughly 1,100 officially confirmed meteorite falls in modern history. Of those, only about 60 are HEDs. That is a rate of roughly 1 HED fall per decade in any given country. 2 in 9 days, on 2 different continents, from 2 different sky directions, is the kind of cluster that statisticians would normally call a fluke. Except the Society's analysis ruled out the fluke explanation. The arrival directions were 98 degrees apart in the sky, which means the 2 rocks were not traveling together. They were not pieces of a single object that had broken up. They were independent. Their orbits had crossed Earth's path at roughly the same time by what should have been pure chance. The odds of 2 independent HED falls landing within 9 days, given the historical rate, work out to roughly 1 in several 100,000. That number alone would not be enough to draw conclusions, but pair it with the broader fireball surge, the doubling of large events, the daytime bolides, and the geographic spread, and a pattern starts to form. Something appears to have stirred up the Vesta family. A gravitational nudge, a recent collision in the asteroid belt, a slow-moving debris cloud, finally reaching Earth's orbit after a long journey inward. Any of these could explain why HED material would suddenly start arriving in unusual numbers. The science of asteroid family dynamics moves slowly. To know for certain whether the Vesta family is the source of the 2026 surge, researchers would need to backtrace the orbits of every recovered fragment and look for a common origin point in the asteroid belt. That work takes months. It involves modeling the gravitational interactions of millions of rocks over millions of years. For now, the Vesta hypothesis is one of the leading candidates. The chemistry fits, the timing fits. The arrival directions are consistent with material drifting in from the inner edge of the asteroid belt. What the hypothesis cannot yet explain is why now, why this spring, why this particular wave. That answer might lie in something much closer to home than the asteroid belt. It might lie 93 million miles away, on the surface of the Sun. Hold a diogenite in your hand, and you are holding something older than Earth's continents, older than its oceans, older than the line between living and not living on this planet. These rocks formed roughly 4.5 billion years ago in the same dust cloud that condensed to make our Sun and its planets. While Earth was still a churning ball of magma with no solid surface, Vesta was already cool enough to have a crust. And that crust, layered with crystalline minerals and shot through with veins of older rock, is what the HED meteorites preserve. The three names in the HED family describe three different depths inside Vesta's ancient body. Eucrites came from the outer crust, the part closest to space. Diogenites came from deeper, from a layer below the crust where the minerals had time to grow into larger crystals. Howardites are mixtures of the two, jumbled together by ancient impacts. To find any of the three on Earth is to hold a slice of Vesta's interior, blasted out by an impact 1 billion years ago, and finally arriving here after the longest journey imaginable. The German rock pulled out of the field in early March was a diogenite. That means it came from deep inside Vesta, from a layer that almost never reaches Earth in a recoverable form. The Ohio fragment recovered on March 18th was classified as a eucrite from the outer crust, two pieces from two different depths of the same asteroid arriving in the same week, on two continents. The chemical signature of an HED meteorite is unmistakable. Geologists call it the oxygen isotope fingerprint. Every body in the solar system formed with a slightly different ratio of oxygen isotopes, and that ratio acts like a serial number stamped into every rock that ever came from that body. When researchers measure the oxygen isotopes in a freshly recovered meteorite, the number either matches Vesta or it does not. There is no ambiguity. Both the German rock and the Ohio rock matched Vesta cleanly. This is also why the alien spacecraft theory got dismissed so quickly by the Society in its public report. The chemistry of these rocks is consistent with material that has been weathering inside the asteroid belt for billions of years. They have the right cosmic ray exposure ages. They have the right crystalline structure. They have the right mineral inclusions. Nothing about their composition suggests anything other than a perfectly ordinary, perfectly natural fragment of Vesta delivered to Earth by perfectly ordinary orbital mechanics. What is not ordinary is the timing. 2 HEDs in 9 days, a doubled fireball count, a wave of daytime bolides, a signal 3.9 standard deviations above the historical baseline. The chemistry is normal, the volume is not. Roberto Vargas, a resident of Windfall, Ohio, was among the first hunters to find a piece of the Ohio rock. He pulled a dark, pitted fragment out of a stretch of field within the projected debris zone, less than 24 hours after the Lake Erie fireball. Photographs of his find show the characteristic black fusion crust, the rounded edges where atmospheric heat had melted the corners, and the rough interior where the rock had split during entry. A second find came from a woman named Harris, age 70, who discovered a triangular black stone wedged between her garage and her house. She had read somewhere that meteorites should not be touched directly. She picked it up with a napkin and placed it in a jar on her kitchen counter. These stones, sitting on suburban kitchen counters across Ohio and Texas and Germany, are older than every fossil ever found on Earth. They are pieces of a vanished world, and more of them are still falling. The first question every astronomer asked when the surge became obvious was the simplest one. Could this be a new meteor shower? The answer, it turns out, is no, and the reason that answer matters is that it eliminates one of the easiest natural explanations for what is happening. A meteor shower works like this. Earth orbits the Sun on a fixed path. Comets, which are essentially dirty snowballs of ice and dust, leave long trails of debris behind them as they swing through the inner solar system. When Earth's orbit intersects one of those debris trails, our atmosphere plows through the leftover dust. The result is a meteor shower. The Perseids in August, the Geminids in December, the Lyrids in April. Every well-known shower is tied to a specific comet or asteroid that left its trail somewhere along Earth's annual loop. Showers have predictable timing. They arrive in the same weeks every year because Earth crosses the same patch of debris at the same point in its orbit each time around. They have predictable origin points in the sky, called radiants. If you trace the paths of shower meteors backward, they all appear to converge on a single point near a specific constellation. The Perseids radiate from Perseus, the Geminids radiate from Gemini. The Society checked all of these markers against the 2026 surge. The dates did not match any known shower window. The first quarter of any year is normally a quiet period for meteor activity, with no major shower active between the small quadrantids in early January and the Lyrids in late April. March is supposed to be a sleepy month. It was not sleepy. More damning, the radiants did not converge. When researchers traced the entry paths of the Big March fireballs backward into space, the lines pointed in completely different directions. The European bolide on March 8th came from one part of the sky. The Ohio bolide on March 17th came from a different part. The Houston event on the 21st came from yet another. The arrival angles were scattered across nearly 100 degrees of sky. That scattering is the opposite of what a meteor shower looks like. A shower would have produced events all radiating from a tight cluster. The 2026 surge produced events radiating from everywhere. This points to what astronomers call sporadic meteors. Sporadic rocks are not part of any organized stream. They drift in from random directions, the leftover debris of countless ancient collisions in the asteroid belt and the outer solar system. In any normal year, sporadic meteors make up roughly half of all observed fireballs. They are the background noise of the inner solar system. What the data suggests is that the sporadic background has spiked. Not a new shower, not a single fragmenting rock, a diffuse, broad-spectrum increase in the small rocks drifting through Earth's neighborhood. This is harder to explain than a shower would have been. A shower comes from a known source on a predictable schedule. A surge in sporadic activity comes from nowhere obvious. It suggests that something has stirred up the general population of small rocks in the inner solar system, sending more of them on Earth-crossing paths than usual. What could stir up the entire sporadic background? The honest answer is that scientists do not know yet. A recent collision in the asteroid belt could send a wave of new debris inward over the course of decades. A close pass by a large body could perturb thousands of small rocks at once. A long-term gravitational resonance with Jupiter could be funneling material in waves that we have only now begun to detect. Any of these is possible. None is yet proven. And the next theory on the candidate list points not to the asteroid belt at all, but to the Sun itself. The other obvious explanation for the surge is that nothing has changed in space. What has changed is us. In the past decade, the world has filled up with cameras. Every phone has one. Every car has a dash cam. Every doorbell has a sensor. Every commercial building has security footage. The number of pieces of glass pointed at the sky at any given moment is orders of magnitude higher than it was in 2011. You would expect this to produce a slow, steady upward drift in fireball reports. More eyes, more videos, more reports. The Society has acknowledged this effect for years. They built it into their baseline calculations. The historical comparison they used for the 2026 analysis covered the period from 2018 through 2025, after the reporting platform had matured and after smartphone saturation had largely plateaued in the United States and Europe. In other words, the comparison years already account for ubiquitous cameras. If the 2026 surge were a camera effect, it would have been a camera effect in 2024 and 2025 too. It was not. The numbers in those years sat comfortably on the baseline. The deeper reason cameras cannot explain the surge is the threshold effect. Better cameras tend to lift the lower end of the distribution. They reveal fireballs that previously went unrecorded. A dim fireball over a rural area might have gone completely unwitnessed 20 years ago. Today, 3 dashcams might catch it from different angles. That effect would inflate the small event category. The small event category did not move. The Society's data shows that fireball events with 10 to 24 eyewitness reports came in at exactly 21 events in early 2026, which is statistically indistinguishable from every prior year. The bottom of the distribution is flat. What grew was the top. Events with 200 or more eyewitness reports do not depend on dashcams or doorbells. They depend on the rock being big enough and bright enough that thousands of people happen to look up at the right second. You cannot manufacture a 200 report event by adding cameras. The fireball has to be physically large enough to light up the sky over multiple states. There is also the matter of physical evidence. Cameras can inflate reports. The Ohio rock is real, the Texas rock is real, the German diorgonite is real. These stones are sitting in laboratories right now, being analyzed by geologists. They have weights, they have crystalline structures, they have oxygen isotope signatures. No amount of social media activity can place a 1-ton airburst over Houston or a 7-ton airburst over Ohio. And there are the sonic booms. Sonic booms are produced when a rock penetrates deep enough into the lower atmosphere to push a shockwave to the ground. The number of sonic boom events in early 2026 was roughly 1 every 3 days, far above the historical average. Sonic booms cannot be exaggerated by reporting bias. Either windows rattled or they did not. In this case, they did. The Society's published analysis goes one more layer deep. They looked at long-duration sightings, which are events lasting more than 5 seconds. These tend to indicate either very large rocks or very shallow entry angles, both of which produce more energy per event. Long-duration sightings doubled in early 2026 against the historical baseline. That metric has nothing to do with cameras. Every diagnostic that should be camera-independent shows the same signal. The rocks are bigger, the events are longer. The meteorites are real. Whatever is causing the surge, it is not happening in the camera. It is happening in space. Houston deserves a second look because the Texas event was unique in one respect that none of the other March fireballs matched. It produced a confirmed indoor meteorite strike. Most fireballs do not produce recoverable meteorites at all. The vast majority of rocks burn up entirely in the atmosphere, leaving behind only dust and a flash of light. A smaller fraction fragments into pieces that scatter across the ground in a long, narrow zone called a strewn field. Of those, only a tiny minority produces fragments large enough to be found and identified. And of those, an even tinier minority strikes a structure. The Society's records show that indoor meteorite strikes in the United States are rare to the point of historical noteworthiness. There have been only a handful of confirmed cases in the past century. The most famous was a woman in Alabama who was struck by a softball-sized meteorite that crashed through her ceiling while she was napping on her couch. That happened in the 1950s. Cases since then have been even rarer. Sherry James in North Houston is now part of that very short list. The fragment that crashed through her roof was, by her description, roughly the size of a football. The official analysis from the responding fire department and the society confirmed it as a meteorite. The rock had the classic dark fusion crust on its outer surface, the result of brief heating during atmospheric entry. It had the heavy, dense feel of meteoritic iron and stone, distinct from anything that could have fallen from a passing aircraft or a construction site. The math of the Houston event is worth working out, because it tells you something important about how dangerous these airbursts can be. The original rock weighed about 1 ton when it entered the atmosphere. Most of that mass vaporized in the airburst 29 miles above the city. The energy released was equivalent to 26 tons of dynamite. That is roughly the energy of a small tactical missile. Released at altitude, the pressure waves spread out and weakened, rattling windows but causing no broad structural damage. Released closer to the ground, the same energy would have shattered windows across a substantial portion of the metro area. The fragment that made it through the heating and survived to ground level was probably less than 10 pounds in its original form. Even so, it was traveling fast enough at impact to punch through roofing material, drywall, and any furniture that happened to be in its way. The terminal velocity of a small meteorite, after atmospheric braking, is somewhere between 200 and 400 miles per hour. That is fast enough to be lethal if the fragment hits a person directly. Sherry James was lucky. The rock landed on her floor, not on her. The Houston event also illustrates something the society has been quietly emphasizing. The size of these rocks falls within the range that scientists call the routine continuum. A 1-ton meteoroid is normal, a 7-ton meteoroid is at the upper end of normal, but still within the expected range of objects that hit Earth in any given decade. The danger from any single one of these rocks is small. The roof strike was alarming locally but injured no one. The Ohio airburst rattled windows but caused no broad damage. What is unusual is not the size of any individual rock. It is the rate at which the rocks are arriving. One Houston event in a decade is normal. 3 or 4 events of similar scale in 3 weeks is not. And the math continues climbing as you move outward from Houston. The next stop is the strangest pattern in the entire dataset. When researchers stacked the early 2026 fireball data against every other year on record, they noticed something unusual about the shape of the distribution. The surge was not even, it was lopsided. And the way it was lopsided pointed directly at the conclusion that the rocks themselves had grown. To understand the shape, imagine drawing a bar chart. Along the bottom, you have categories of fireballs sorted by how many eyewitnesses reported them. Small fireballs on the left, giants on the right. Now stack 2 years on top of each other. A normal year and the 2026 surge. In a normal year, the chart looks like a steady slope. Many small events, fewer medium events, even fewer large events. A handful of giants. The slope is smooth and predictable. The historical average for the past 15 years matches this pattern almost perfectly. In 2026, the slope warps. The small end is flat, identical to the historical average. The medium end is 63% higher. The large end is doubled. The giant end is doubled. The lopsidedness gets more dramatic as you move toward the right side of the chart. This shape has a name in atmospheric physics. It is called a power law tail expansion, and it has only one natural explanation. The rate of large incoming objects has increased, while the rate of small incoming objects has remained constant. The river of rocks flowing past Earth has not just thickened, it has shifted toward bigger pieces. The mechanism that could produce this pattern is narrow. A single fragmenting parent body would not do it, because that would produce a tight cluster of events from one direction in the sky. A meteor shower would not do it, because showers tend to produce many small fireballs, along with a few larger ones, not a top-heavy distribution. A camera or reporting bias would not do it, because biases lift the small end of the distribution, not the large end. What can produce a top-heavy distribution is a recent disruption somewhere in the asteroid belt that scattered a population of larger objects toward the inner solar system. Imagine a billiards table. A cue ball strikes a tight cluster of balls, and most of them stay in the cluster, but a few get knocked free. The ones that get knocked free tend to be the ones on the outer edge of the cluster, and they travel in unpredictable directions. If you watched a billiards table where this happened repeatedly over millions of years, you would see exactly the pattern the 2026 data is showing. Most rocks stay in the belt. A few get nudged into Earth-crossing orbits, and the ones that get nudged tend to be larger than average. This is consistent with another observation the Society made. The 2026 surge produced an unusual number of objects in the 2-meter size range, which is the upper end of the routine impact distribution. The Ohio rock was 6 feet across. The Houston rock was 3 feet across. The European bolide on March 8th produced a recovered diogenite suggesting an original rock at the upper end of the size scale. These are big stones by historical standards. The fingerprint of the distribution, in other words, points to a recent disturbance in the asteroid belt. The Vesta family signal in the meteorite chemistry points to the same conclusion. Two independent lines of evidence are converging on the same hypothesis. The hypothesis still needs to be proven. The orbital backtracing work to confirm a common origin point is ongoing in research labs across the United States and Europe, but the early signs are pointing to a single recent event somewhere in the inner asteroid belt that may have sent a wave of fragments toward Earth. The next chapter explains what that wave looks like up close. 250 tons of dynamite released in a single instant, 30 miles above an Ohio town. The numbers attached to the Ohio bolide are worth pausing on because they let you feel the scale of what happened on the morning of March 17th. The rock entered the atmosphere weighing 7 tons. It was traveling at 40,000 miles per hour. The kinetic energy of that rock, calculated by squaring its velocity and multiplying by its mass, came out to roughly 250 tons of dynamite equivalent. That is the energy that was released in less than 1 second, 30 miles above the small Ohio town of Valley City. To make that number physical, imagine the following. 250 tons of dynamite is the explosive yield of a small tactical weapon. It is roughly 50 times the energy released by the largest conventional bomb dropped in modern warfare. If you set it off at ground level in a populated area, you would flatten everything within several blocks. The shockwave would shatter windows for half a mile in every direction. The flash would be visible for 100 miles. Released at 30 miles up, the same energy spreads through a thicker column of air and weakens dramatically before it reaches the ground. By the time the pressure wave got to Cleveland, it had attenuated to the strength of a sharp rolling thunderclap. By the time it got to Pittsburgh, it was a distant rumble. By the time it got to Detroit, it was barely audible. This altitude buffer is the single most important reason these airbursts almost never kill anyone. The atmosphere acts as a shield. It heats the rock up. It tears it apart. It absorbs most of the released energy in the form of light, heat, and a spreading shockwave that loses force as it travels. By the time the energy reaches the ground, it is a fraction of what it was at the moment of fragmentation. The Tunguska event of 1908 is the comparison point that scientists usually reach for. In June of that year, a small asteroid or comet fragment entered the atmosphere over a remote part of Siberia and exploded about 5 miles above the ground. The energy released has been estimated at somewhere between 3 and 15 megatons of dynamite equivalent. That is 1,000 times more energy than the Ohio bolide. The Tunguska blast leveled around 800 square miles of forest. Trees were knocked flat in a radial pattern pointing outward from the blast center for 50 miles in every direction. If the same event had happened over a major city, the city would not have survived. The Ohio bolide was nowhere near Tunguska scale, but it was the largest confirmed airburst over the continental United States in recent years. And it followed by only 9 days a European event of comparable size, and was followed 3 days later, by a smaller but still substantial Houston event. 3 airbursts in 2 weeks, all in the energy range between 25 and 250 tons of dynamite equivalent. The historical average for events in that size range over a similar geographic footprint is roughly 1 or 2 per quarter, not 3 in 2 weeks. This is what the Society means when it says the distribution has shifted. The big events are not just more numerous, they are arriving in clusters that look almost coordinated, even though the orbital mechanics make any actual coordination impossible. The rocks are not communicating. They are simply arriving more frequently because more of them are out there. How many more is the question that nobody can yet answer. The Society's data captures only what hits Earth. The rocks that miss us entirely are tracked by separate networks run by NASA and the European Space Agency, and those networks have their own troubling story to tell about the spring of 2026. Buried in the official NASA materials on the 2026 surge is a quiet line from one of the most respected scientists in the field. It is worth reading carefully because it tells you something about how much the experts actually know. Bill Cook runs NASA's Meteoroid Environment Office. His job is to track the population of small rocks that pose a threat to spacecraft, satellites, and occasionally the surface of the Earth itself. He has been doing this work for years. He has access to telescope networks, radar data, satellite observations, and the full archive of CNEOS bolide records. In a NASA explainer published on March 26th, Cook's office acknowledged the existence of what astronomers have long called fireball season. The phrase refers to a roughly 2-month window every spring, from February through April, during which the rate of bright meteor appearances climbs by 10 to 30% above the annual baseline. This pattern has been observed for decades. It is consistent across many years of data. It is not a one-time event. It is a recurring seasonal feature of Earth's orbital path. Here is the part that matters. NASA does not know why fireball season happens. The explainer published in March uses the phrase, in essence, that the seasonal climb occurs for reasons we do not fully understand. That admission has been on the record for years. It is not new. What is new is the context in which it appears now. If NASA does not fully understand the baseline pattern of fireball season, then the baseline against which 2026 is being measured is itself only partially mapped. The historical average is a number we can calculate. The mechanism that produces that average, the orbital geometry or the gravitational resonance, or the seasonal alignment that funnels more rocks toward Earth in spring than in fall, is not fully nailed down. There are several leading hypotheses. One involves Earth's orbit passing through a denser region of the inner solar system during spring, picking up more small bodies as we move through it. Another involves the gravitational influence of Jupiter creating long-period waves of debris that wash through the inner system on a seasonal cycle. A third involves the orientation of Earth's axis relative to the plane of the asteroid belt, which changes slightly with the seasons and may affect detection rates more than actual flux rates. None of these has been confirmed. What this means in practical terms is that when scientists say the 2026 surge sits 3.9 standard deviations above the historical mean, they are comparing this year against a baseline whose own causes are partially mysterious. The anomaly is real. The question of what produced it is layered on top of a baseline question that is itself not fully resolved. This is one of those moments in science where the honest answer is that the experts know enough to identify a problem, but not enough to explain it. The Society's report is direct about this. NASA's explainer is direct about this. Independent analysts working with the CNEOS archive are direct about this. Everyone agrees that something is happening. Nobody agrees on what. There are reasons to take this admission seriously, rather than panic over it. The objects involved are still within the size range that Earth encounters routinely. No telescope network has detected a large incoming asteroid that poses any near-term threat. The seasonal pattern has been observed for decades without causing damage on a wide scale. The 2026 surge is anomalous in the historical record, but its absolute danger remains small. What it changes is how confidently anyone can claim to understand the small body population near Earth. The honest answer right now is that we know less than we thought we did, and that admission may be the most important fact in this entire story. The next chapter goes deeper into how the catalogue of bolide records came to be, and why the data we are using now is better than anything available even 10 years ago. For decades, the most complete record of large fireball events on Earth was a secret. The United States Space Force and its predecessor agencies operated a network of military sensors designed to detect nuclear detonations from orbit. Those sensors were optimized to catch the bright flashes of nuclear explosions. They turned out to catch something else just as reliably. They caught fireballs. Any object entering the atmosphere at high speed produces a bright optical flash and a measurable infrasound signature. The same sensors that watched for nuclear weapons could also identify a meteoroid airburst with high precision. Over decades of continuous operation, the military accumulated a detailed catalogue of bolide events worldwide. The data included date, time, location, peak brightness, and total energy released. It was a goldmine for asteroid science. For most of the catalogue's history, it was not available to civilian researchers. National security concerns kept the records classified. Scientists outside the defense community knew it existed, but had no access. The civilian record of large fireball events relied on a patchwork of eyewitness reports, occasional radar detections, and the smaller data sets maintained by academic institutions and amateur organizations like the American Meteor Society. In 2022, the Space Force declassified decades of bolide data and transferred it to NASA. The transfer expanded the civilian catalogue substantially. Records that had been collected continuously since the 1980s suddenly became available for public analysis. NASA folded the data into its Center for Near-Earth Object Studies, known as CNEOs, and made the records searchable through a public archive. The release transformed the field. For the first time, researchers could pull a structured record of large fireball events going back decades and analyze trends with real statistical power. The catalogue now logs impact energy in kilotons of dynamite equivalent, entry velocity altitude of peak brightness, and geographic coordinates. Each entry is derived from light curve analysis, a technique in which sensors measure the brightness of a fireball over time and convert that optical signature into an estimate of the rock's kinetic energy. The 2026 anomaly was identified in part by independent analysts who pulled records from this expanded CNEOS archive. They filtered by date range and energy threshold. They compared early 2026 totals against the historical distribution. The 3.9 standard deviation figure came out of that analysis. The calculation is reproducible. Anyone with basic data skills and access to the public archive can verify it. There is a caveat worth being honest about. The catalogue is not complete. It covers only the brightest events, the ones that triggered the military sensors. Smaller fireballs that produced flashes below the detection threshold are not in the records. Sensor capabilities have improved over the years, which means more recent events are detected with higher precision than older events. The 2022 declassification expanded the available records significantly, which means the apparent rate of fireball events appears to climb partly because we have better data, not just because we have more rocks. This is the central question that researchers are still working to answer. How much of the 2026 signal is a real increase in incoming material, and how much is an artifact of better detection? The Society's analysis tries to control for this by using only data from 2018 onward, when the reporting platform was already mature. The CNEOs-based analysis tries to control for this by focusing on the largest energy classes, where detection has been near saturated for decades. Both approaches still leave some uncertainty. The honest summary is that the signal appears real, the detection improvements are real too, and the precise size of the genuine anomaly will not be fully known until more analytical work is published. The Space Force release made the question askable. The next round of research will determine the answer. And the answer may involve one more source of uncertainty, a source that no telescope can see clearly, a source that hits Earth from the direction of the sun itself. If the 2026 surge is not a meteor shower, and the radiants do not converge, then the rocks must be sporadic. They must be drifting in from random directions, the leftover background noise of the inner solar system. That sounds like a simple answer. It is anything but. Sporadic meteors are the hardest category for scientists to study. They have no known parent body. They have no predictable arrival schedule. They have no consistent direction in the sky. They are the cosmic equivalent of strangers wandering past your house, untraceable to any particular neighborhood. In a normal year, sporadic rocks account for roughly half of all observed fireballs. The other half belongs to organized streams, the meteor showers tied to known comets and asteroids. What the 2026 data shows is a spike in the sporadic half. The known showers have stayed quiet. The quadrantids in January produced normal rates. No other major shower was active during the surge window. The rocks that lit up the sky over Vancouver, Europe, Ohio, Houston, and California came from a scattered population, not a single stream. That fact narrows the possible sources, but it also makes the science harder. A single stream has a single parent body. Track the stream, find the body, and you have your answer. A diffuse sporadic background has many parent bodies, scattered across the inner solar system, each contributing a small fraction of the total. To track the surge to its source, researchers would need to backtrace dozens or hundreds of individual rocks and look for patterns in their orbital histories. That work is being attempted right now. Several research groups are running simulations that take the known orbits of the recovered meteorites and run them backward in time. The goal is to find a common origin point in the asteroid belt where the trajectories converge. If such a point exists, it would represent a recent collision or a recent gravitational disturbance that scattered material toward Earth. The early simulations are pointing in interesting directions. The two HED meteorites recovered from Germany and Ohio both backtrace to the inner asteroid belt, consistent with the Vesta family. The other recovered fragments are less precisely characterized, but appear to come from the same general region. If the pattern holds, the 2026 surge may be the leading edge of a wave of debris from a single recent event in the asteroid belt, possibly a collision among Vesta family members that scattered fresh fragments inward. This kind of wave is not unusual in the long-term history of the solar system. The asteroid belt is full of debris streams that wash through the inner planets on timescales of hundreds of thousands or millions of years. What is unusual is the timing. To be detecting a wave like this in real time, in the middle of its arrival, is exceptionally rare. Most debris streams take centuries to fully pass through Earth's orbit. The leading edge of a wave can build for years before the peak arrives. If the leading edge hypothesis is correct, the 2026 surge would not be a one-time event. It would be the beginning of a multi-year elevated rate. The spring of 2027 would show similar elevations. The spring of 2028 would too. The pattern would persist for as long as Earth continued to cross through the debris zone. This is the question that researchers are now racing to answer. Is the surge a single spring of unusual activity, or is it the front edge of something larger? The answer will not be known until the spring of 2027, when the next round of data will either confirm the pattern or dissolve it. If it confirms, the implications are substantial. A sustained elevation in large fireball events means more meteorite falls, more sonic booms, more rooftop strikes, and a higher probability of an event large enough to cause real damage. The probability remains small in any given year. But the population of risk does not stay flat. The sun itself may yet have something to say about all of this. To understand what may be happening, Picture a slow-motion explosion that started 1 billion years ago and is only now reaching us. The Vesta family hypothesis goes like this. Roughly 1 billion years ago, something massive struck the south pole of Vesta and carved out the enormous crater that NASA's Dawn spacecraft photographed in 2011. The impact was so violent that it ejected about 1% of the asteroid's total mass into space. Some of that mass stayed in tight orbits near Vesta itself, some drifted outward, and some, over the slow churn of gravitational nudges and orbital resonances, drifted inward toward the inner solar system. The inward drift takes a long time. Asteroid debris does not travel in straight lines. It bounces between the gravitational fields of Jupiter, Mars, and the Sun, sometimes losing energy and falling closer to the Sun, sometimes gaining energy and being flung outward. A piece of Vesta ejected 1 billion years ago might have spent most of the last 1 billion years in the asteroid belt, only recently entering an orbit that crosses Earth's path. The hypothesis researchers are now testing is that a more recent event, perhaps a collision between two Vesta family members within the last few million years, scattered a fresh wave of fragments inward. That wave would have taken anywhere from tens of thousands to millions of years to fully reach Earth's orbital zone. The leading edge of the wave would be arriving now. If true, the timing is extraordinary. To witness the front of a debris wave from a deep belt collision is the kind of event that happens once in a long while. Most of human history has unfolded between waves. To be alive during the arrival of one is, in cosmic terms, a coincidence of remarkable scale. The evidence pointing toward this hypothesis is circumstantial but consistent. The recovered HED meteorites have oxygen isotope signatures that match Vesta. The arrival directions of the two main HED events are different enough to rule out a common parent in the recent past, suggesting the source is a diffuse population rather than a single fragmenting rock. The shape of the size distribution favors a recent disruption rather than a steady background. The orbital backtracing work is the missing piece. Researchers are running simulations that take the velocity and entry angle of each recovered fragment and project backward through time. Accounting for the gravitational influences of the Sun, the planets, and Jupiter in particular, the simulations produce a probability cloud of possible origin points. If the clouds from multiple fragments overlap in a tight region of the asteroid belt, that overlap would be strong evidence for a common source. Early results from these simulations have not been published in peer-reviewed form yet. Preliminary discussions at meteoritics conferences in late March suggested that the overlaps are real, but tentative. The data needs more time, more recovered fragments, and more refined orbital reconstructions before any source region can be confirmed. If the source is eventually identified, it would represent one of the most precise links ever established between a contemporary fireball wave and a specific event in the asteroid belt. It would also have predictive value. If the wave is real and its source is known, researchers could estimate how long the elevated rate will last, how much more material is in transit, and when the peak might arrive. For now, the Vesta hypothesis remains a leading candidate, but not a confirmed answer. The chemistry fits. The numbers fit. The timing fits. What is missing is the orbital fingerprint that would close the case. And while that work continues, another line of investigation is pointing in a completely different direction, toward the Sun. Earth is currently in the active phase of what astronomers call solar cycle 25. The Sun goes through these cycles every 11 years or so, building from a quiet minimum to a violent maximum, and back again. The current cycle is near its peak. Sunspots are abundant. Solar flares are frequent. Coronal mass ejections, the enormous bubbles of charged particles that the Sun occasionally hurls into space, have been hitting Earth's magnetic field on a regular basis. A few analysts have noticed that this peak activity coincides with the 2026 fireball surge. They have proposed a hypothesis. Could the solar weather be nudging small rocks in the inner solar system, perturbing their orbits in subtle ways that send some of them onto Earth-crossing paths? The physics behind this hypothesis is not as far-fetched as it might sound. Small particles in space, including the dust and pebbles that produce the smaller meteor showers, are affected by solar radiation pressure. Sunlight carries momentum. When that momentum hits a small rock, it pushes the rock slightly outward, away from the sun. The effect is tiny on any single particle, but over years and decades it can change the orbit of a small body in measurable ways. For larger rocks in the range of 1 ton or 7 tons like the ones falling in 2026, the solar radiation effect is much weaker. These rocks have too much mass for sunlight to push them significantly. The pressure of solar wind, the stream of charged particles flowing outward from the sun, is even weaker as a force on dense rocks. To move a 7-ton asteroid by solar pressure would require timescales of millions of years. A coronal mass ejection is different. When the sun releases a massive burst of charged particles, the burst can carry energies high enough to interact briefly with small bodies in the inner solar system. Some analysts have speculated that a strong enough event could nudge a minor meteoroid stream into a slightly different geometry, just enough to change whether or not Earth crosses that stream's path in any given year. The hypothesis is testable in principle. Researchers would need to cross-reference the timing of coronal mass ejections from solar observatories with the appearance of bolides in the CNEOS catalogue. If certain bolides cluster within days or weeks of specific solar events, that would suggest a connection. If they do not, the hypothesis would be weakened. The work has not yet been done in published form. Preliminary discussions among amateur analysts suggest possible correlations, but the small sample size and the difficulty of separating cause from coincidence have prevented any firm conclusions. Real-time data from solar observatories, like the Solar Dynamics Observatory, is available. The CNEOS catalogue is available. The analysis is straightforward in principle. Until it is done rigorously, the solar connection remains an idea, not an answer. There is a more general version of the same hypothesis. The sun's magnetic field shapes the inner solar system in ways that influence the population of small bodies on timescales of decades. During solar maximum, the heliosphere expands and the structure of the interplanetary magnetic field becomes more complex. Some researchers have proposed that this complexity changes, which small bodies get nudged into Earth-crossing orbits. If true, the surge in 2026 would correlate roughly with the peak of solar cycle 25. Past peaks should show similar effects in the historical record. Past minima should show fewer fireballs. The CNEOS catalogue is just barely long enough to test this. Solar cycle 24 peaked around 2014, and the fireball data for that year does not show a comparable spike. Solar cycle 23 peaked around 2000, before the digital catalogue was mature. The historical evidence for a solar driver is weak so far. The most honest assessment is that the sun's role in the surge is unproven. It is one of several hypotheses being considered. Until the cross-referencing work is published, it remains a candidate rather than an explanation. What is more striking than any single hypothesis is the geographic scope of the surge. The rocks are not falling in one part of the world, they are falling everywhere. March 23rd was a Monday. The skies over the state were clear and dry, the kind of late winter California afternoon that promises an ordinary week ahead. And then, in a span of a few hours, 2 separate fireballs crossed the sky over different parts of the state. Both were bright enough to draw substantial witness reports. The first crossed the northern part of the state in the early afternoon. The second crossed the southern part later that day on a different trajectory. The Society's analysis confirmed that the 2 events were independent. They were not pieces of a single fragmenting rock. They came from different orbital directions. They simply happened to arrive on the same day, over the same state, hours apart. This kind of clustering is what statisticians find difficult to dismiss. The probability of 2 independent fireballs of significant size crossing the same state on the same day, given the historical rate, is roughly 1 in several hundred. Not impossible, just unusual. When you add it to the other clusters that occurred in March, the cumulative probability of the entire pattern occurring by chance climbs toward the figure that researchers eventually calculated: 1 in 20, 1,000. California had been quiet in the months leading up to the double event. The state's fireball detection network had logged a normal rate of small events through January and February. The March cluster came without warning, 2 bright streaks on the same Monday, and then back to baseline rates the following week. This is the pattern that emerges across the whole 2026 surge. Quiet stretches punctuated by sudden clusters. Vancouver in early March, Europe a few days later, France and Spain 3 days after that, Ohio 6 days after that, Houston 4 days after Ohio, California 2 days after Houston. Each event came from a different direction in the sky. Each was independent of the others, and yet they kept arriving in a rhythm that felt almost like a wave breaking on a long beach. If you mapped the entry directions of all the major March events on a sky chart, you would see lines radiating from many different points. There is no single radiant. There is no obvious cluster. The events are scattered across the celestial sphere, as if the inner solar system itself had grown noisier. This is one of the strongest pieces of evidence that the surge involves the diffuse sporadic background rather than a single new stream. A stream would have produced a cluster of arrival directions. The actual pattern shows the opposite. The arrivals are coming from everywhere at once. For residents on the ground, the geographic spread meant that no part of North America or Europe felt immune. People in Texas watched their windows rattle. People in Ohio heard the morning sky crack open. People in California saw bright streaks twice in one day. People in Germany and France watched a 5-second daytime fireball longer and brighter than anything in living memory. The surge was not a regional event. It was a hemispheric one. The Society's published analysis noted this explicitly. The geographic distribution of the events was inconsistent with any localized source. The reports came from across North America, Europe, and parts of Asia. Sonic booms were logged in multiple countries. Infrasound detectors in widely separated locations picked up signatures from the same individual events, confirming that the rocks were broadly distributed across the globe. A localized cluster might suggest a single dust cloud passing through one part of Earth's orbit. A global pattern suggests something larger. It suggests that the entire population of small rocks crossing Earth's orbital path has shifted, and that the shift is uniform across all the longitudes Earth's atmosphere intercepts as the planet rotates. This is what worries researchers most, not the absolute danger from any single rock, the pattern itself. And the question that pattern raises is one the Society had to address head-on in its public report: the question of whether any of this could be artificial. The Society addressed the alien hypothesis directly in its published report, and the answer was unambiguous. The rocks are not artificial. The chemistry is wrong. The trajectories are wrong. The behavior is wrong. Every diagnostic that scientists used to distinguish natural objects from possible artificial ones came up consistent with natural origin. It is worth walking through the logic, because the alien speculation has been loud on social media, and the answer deserves to be clear. Natural meteorites have specific chemical signatures that form only inside large bodies over geological timescales. The crystalline structures in an HED meteorite, for example, can only form inside a differentiated asteroid, where heat and pressure have separated the original primordial material into distinct mineral layers. The oxygen isotope ratios in these stones match what we expect from objects that formed alongside the rocky planets in the early solar system. The cosmic ray exposure ages, calculated from the buildup of certain isotopes that only form when a rock is exposed to cosmic radiation in space, are in the millions to hundreds of millions of years. None of these properties can be faked or manufactured. The German diogenite and the Ohio eucrite both passed all of these tests cleanly. They are unambiguously natural fragments of Vesta. They have been weathering inside the asteroid belt for billions of years. Their chemistry is well understood and entirely consistent with their natural origin. Trajectory analysis tells the same story. Artificial objects, if they existed, would show signs of controlled flight. They would change direction, they would decelerate when they should accelerate. They would maintain stable trajectories that defy the physics of passive motion. The 2026 fireballs showed none of these properties. Every one of them followed a ballistic trajectory consistent with passive entry of a natural rock under the influence of gravity and atmospheric drag. The Ohio rock moved southeast at 40,000 miles per hour and decelerated exactly as physics predicted. The Houston rock airburst at 29 miles up exactly where physics predicted it would. There were no anomalies. The behavior of the fragments after entry also fits natural patterns. The breakup zones, the strewn fields, the orientation of the recovered stones relative to their entry paths. All of these match what scientists have observed in hundreds of previous natural events. Nothing about the fragmentation patterns suggests artificial composition or controlled deployment. Finally, the Society addressed the question of trajectory clustering. If a coordinated artificial source were releasing objects into Earth's atmosphere, the arrival directions would show patterns. They would suggest a release point, a common origin in space. The actual data shows scattering across nearly the entire celestial sphere. The events are coming from everywhere, which is exactly what you would expect from a diffuse population of natural rocks, and exactly what you would not expect from a single artificial source. The Society's report concluded that there is no evidence of anomalous trajectory behavior, controlled flight, or non-natural composition. That language is careful. It says the evidence is absent, not that the question was not asked. The question was asked. The answer was negative on every diagnostic. This is a useful counterweight to the speculation that inevitably accumulates around any unusual celestial event. The fireball surge is strange. The data is anomalous. The cause is genuinely unknown. None of those facts implies an artificial explanation. The same data that makes the surge mysterious also makes it definitively natural. A mystery in cause is not the same as a mystery in nature. What remains is a natural phenomenon producing more activity than its historical baseline. That is rare. It is interesting. It is worth investigating. It is not aliens. The investigation has tools that did not exist 20 years ago. One of them does not use the sky at all. It uses the ground itself as a giant ear listening for the rumble of fireballs from across continents. The most surprising tool in modern fireball detection is not a telescope. It is a microphone. When a large rock enters the atmosphere, the energy it releases produces a pressure wave that travels outward through the air at the speed of sound. The wave starts as a sharp crack near the entry point. As it spreads, it stretches into a longer, deeper rumble. Most of the high-frequency components dissipate within the first few hundred miles. What remains is a very low-frequency wave, far below the range of human hearing, that can travel for thousands of miles before fading. These low-frequency waves are called infrasound. The frequencies involved are typically below 20 Hz, which is the lower limit of what human ears can detect. We cannot hear infrasound directly, but specialized microphones can. And those microphones can be placed thousands of miles apart and still pick up the same event. A global network of infrasound stations was originally built for a very different purpose. The Comprehensive Nuclear Test Ban Treaty Organization operates a network of monitoring stations designed to detect underground nuclear tests anywhere on Earth. Nuclear detonations produce powerful infrasound signatures. The network was built to listen for those signatures and confirm any treaty violations. It turns out that the network also picks up fireballs. Every large bolide that enters the atmosphere produces an infrasound signature similar to a small nuclear explosion. The Ohio rock, with its 250-ton dynamite equivalent, registered cleanly on multiple infrasound stations across North America. The European bolide on March 8th registered on stations across Europe and parts of North Africa. The Houston event registered on stations as far away as the Caribbean. By comparing the arrival times of the same wave at different stations, researchers can triangulate the location and altitude of the airburst with remarkable precision. They can also estimate the total energy released because the strength of the infrasound signature scales with the explosive yield of the event. This is how the Society and NASA arrived at the 250-ton figure for the Ohio bolide. The infrasound networks heard it and reported a consistent answer from multiple directions. The geographic spread of the 2026 infrasound detections is itself part of the evidence for a broad pattern. If the surge had been a localized phenomenon, the infrasound stations would have shown clustered detections in one region of the world. Instead, the detections span North America, Europe, and Asia. The same instruments that confirm the bolides are real are also confirming that the bolides are distributed globally. This is the kind of corroborating evidence that makes researchers confident the signal is genuine. Eyewitness reports can be exaggerated, cameras can be misinterpreted, social media can amplify normal events into apparent anomalies. Infrasound cannot. The pressure waves are objective. They either exist or they do not. They either match the predicted energies or they do not. The match has been clean for every major event of the 2026 surge. There is one more thing infrasound detection does that nothing else can. It works at night, during the day, through clouds, and across continents. It does not depend on people looking up. It does not require clear skies. It catches events that would otherwise go unrecorded, including daytime bolides over remote ocean areas where no eyewitnesses are present. The fact that the infrasound networks have logged an elevated rate of large signatures in early 2026 is independent evidence that the surge is real, regardless of how many people happen to file reports. The hunt for the rocks that produced those signatures continued on the ground. And in the cornfields of Ohio, the search turned into something that looked almost like a gold rush. Within 24 hours of the Ohio bolide, the meteorite hunters arrived. These are mostly amateurs. Some are retired engineers. Some are professional collectors. Some are university researchers who get on planes the moment NASA releases a strewn field map. They share a common obsession with finding fragments of recent falls before the weather destroys them or the local landowners refuse to grant access. The economics drive the urgency. A freshly fallen meteorite, with its glassy black fusion crust still intact and its interior chemistry uncontaminated by earth, water, or microbes, can be worth several hundred to several $1,000s per gram. A fragment the size of a baseball can sell for tens of thousands of dollars. A rare classification like the HED family can multiply those numbers. The Ohio rock, classified as a Euclid, is among the most valuable meteorite types per gram by weight. The strewn field, the long elongated zone where fragments of a fragmenting bolide are likely to have fallen, was estimated by NASA to lie south of the Valley City fragmentation point. The probable zone extended through parts of Medina County and into the rural farmland between Akron and Canton. The terrain is a patchwork of cornfields, hayfields, small woods, and rural residential areas. Most of it is privately owned. Most of it is muddy in March. Roberto Vargas of Windfall, Ohio, was among the first to score a find. He pulled a small dark fragment out of the projected debris zone less than a day after the fireball. Photographs showed the classic fusion crust, the rounded edges, and the rough interior surface where the rock had broken during entry. The find made local news. Within days, dozens of hunters were combing the fields with metal detectors, magnets, and trained eyes. A retired business owner named Harris was the second confirmed find. She is 70 years old. She did not go looking for a meteorite. She walked out to her driveway one morning and noticed a black stone wedged in a small space between her garage and her house. The stone was somewhat triangular, less than 2 inches across, very black, with pits and grooves and a melted texture on the outside. She had read that meteorites should be handled with care, so she picked it up with a napkin and placed it in a jar on her kitchen counter. Her instinct was right. Direct contact with human skin oils can introduce contaminants that compromise the scientific value of a freshly fallen stone. The Society and most research institutions recommend that any suspected meteorite be photographed in place, documented with GPS coordinates, and lifted only with a clean tool like a napkin, glove, or plastic bag. Heat exposure should be avoided. Magnets should not be used because they can disrupt the magnetic record preserved inside the rock. The hunters who arrived in the days after the Ohio fall worked under intense competitive pressure. Every day that passed brought more rain, more snow, more wind, and more risk that fragments would be weathered or buried. Some hunters worked with drones to scan large open fields from the air. Others walked the projected strewn field lines methodically, sweeping the ground in a grid pattern. The scientific value of the recovered fragments goes far beyond their dollar price. Each stone is a sample of asteroid material that is being delivered to Earth at almost no cost. A NASA mission to retrieve the same kind of sample from Vesta itself would cost billions of dollars. A meteorite recovered from an Ohio cornfield, classified within days and analyzed within weeks, provides the same information for free. The science alone is worth the muddy boots. By late March, several confirmed fragments had been recovered from the Ohio-strewn field. The Society and university researchers were already working on the chemical analysis. The early classification as a eucrite confirmed the Vesta family origin. Further analysis would refine the source region within the asteroid belt and possibly pin down the orbital history of the parent body. Across the Atlantic, a similar hunt was underway in Germany, and the German story would prove just as remarkable. The March 8th European bolide produced the most witnessed fireball in the Society's history. It also produced one of the most fortunate meteorite recoveries of the past decade. The bolide entered the atmosphere on a long, shallow trajectory across Central Europe. It crossed France, Germany, Switzerland, Belgium, and the Netherlands during its 5.5-second visible flight. Most of the original rock vaporized in the airburst. Some of the larger fragments survived and continued downrange, falling along an elongated strewn field that extended across parts of central Germany. One of those fragments did exactly what the Houston fragment did 2 weeks later. It crashed through a roof. The German home was in a small village in the projected strewn field zone. The fragment punched through the roof tiles, broke a ceiling beam, and landed in an interior room. Nobody was hurt. The homeowners called the local authorities, and within hours, the stone was in the hands of researchers from a nearby university. The fast recovery meant the meteorite was on its way to a laboratory before any significant terrestrial weathering could occur. That kind of pristine recovery is extremely rare. The classification came back as a diogenite. The diogenite category is the deepest member of the HED family, formed in a layer below Vesta's outer crust, where the minerals had time to crystallize into larger structures than the eucrites above. A freshly recovered diogenite is one of the rarest meteorite types in the world. Fewer than 100 confirmed diogenite falls exist in the entire historical record. To find a fresh diogenite from a known fireball event, with the exact entry trajectory documented and the recovery occurring within hours of the fall, is the kind of event that meteorotics researchers wait years to encounter. The German fragment immediately became one of the most studied diogenites in scientific collections. The chemistry came back consistent with Vesta. The oxygen isotope ratios matched. The mineral inclusions matched. Every test confirmed that the stone had spent the last billion years as part of the broader Vesta family in the asteroid belt before its journey inward toward Earth. The German recovery and the Ohio recovery, taken together, established the Vesta connection beyond reasonable doubt for the two largest events of the March surge. Both rocks came from Vesta. Both had been weathering in the asteroid belt for vast spans of time. Both arrived at Earth within 9 days of each other, from arrival directions 98 degrees apart. The orbital implications, as we have discussed, are extraordinary. The German recovery also illustrated something important about the global infrastructure for handling meteorite falls. European authorities have well-established protocols for working with university researchers when a fall is reported. The chain of custody from the impact site to the laboratory is short and well managed. In the United States, the protocols are more variable, but the Society and several research institutions have built relationships with regional authorities that allow for fast recoveries in most cases. This infrastructure matters because the scientific value of a fresh fall degrades quickly. Water exposure, biological contamination, and terrestrial weathering all begin within hours of an impact. A stone recovered within a day and stored properly retains nearly all of its original chemistry. A stone recovered after a month in a wet field may have lost critical isotope ratios that would have helped determine its orbital history. The German diogenite was recovered fast enough that almost every original property was preserved. The Ohio eucrite was recovered within hours by a homeowner who knew enough to call the right people. Both stones are now contributing to the scientific understanding of the broader surge in ways that would have been impossible if either had been left to weather for a few weeks. And while researchers worked in laboratories, another part of the story was unfolding in plain sight. The daytime fireballs of March were doing something that almost never happens. They were turning daylight into a stage. Imagine a field of corn stubble stretching to the horizon, dusted with early spring frost, the rows running straight east to west. Somewhere in that field, a piece of an asteroid has been waiting for several days to be found. This is what a meteorite-strewn field looks like in practice. It is mundane, it is muddy, and it is one of the more scientifically valuable patches of ground on Earth in the days following a major fireball event. A strewn field forms because incoming meteoroids almost always fragment during entry. The pressure of atmospheric heating tears the rock apart. The fragments continue forward on slightly different trajectories, each one decelerating at a different rate, depending on its size, shape, and mass. Larger fragments tend to maintain more momentum and travel farther downrange. Smaller fragments lose speed faster and fall closer to the breakup point. The result is a long, narrow zone on the ground where fragments are likely to be found. The zone is shaped like a thin ellipse, oriented along the entry trajectory. Larger pieces concentrate at the downrange end, smaller pieces and dust scatter toward the upper end. For the Ohio event, the strewn field extended for several miles south of the Valley City fragmentation point, with the largest expected fragments falling near the southern end of the zone. NASA published a probable strewn field map within hours of the bolide. The map is generated by combining the entry trajectory, the altitude of fragmentation, the estimated mass and shape of the parent rock, and the local wind patterns at the time of the fall. The result is a probability map showing where fragments are most likely to be on the ground. The map is not a guarantee. Fragments can fall outside the projected zone, particularly if unusual atmospheric conditions affected their descent, but the map gives hunters a starting point. The cornfield environment is in many ways ideal for meteorite recovery. The vegetation is short or absent in early spring. The soil is bare or stubbled. A dark rock with a fresh fusion crust stands out clearly against a light brown field. The wide-open terrain allows hunters to scan large areas efficiently, either on foot or with drones. The fields are private property. Permission must be obtained from the landowner before any search can begin. Some landowners welcome hunters and even charge modest access fees. Others refuse entry entirely, sometimes for fear of liability or property damage. The society and regional astronomy clubs typically coordinate with local landowners to facilitate access where possible. Once a fragment is found, the documentation process matters as much as the recovery itself. The society recommends that hunters photograph the find in place, record the exact GPS coordinates, and document the surrounding terrain before any movement of the stone. This documentation allows researchers to reconstruct the spatial distribution of the strewn field across all recovered fragments, which provides information about the size and shape of the original parent rock. The Ohio strewn field produced several documented finds in the days and weeks following the fall. The total recovered mass is still being counted as more fragments come in. Many of the early finds were small, in the range of a few grams to a few ounces. Larger fragments may still be on the ground, awaiting discovery in fields that have not yet been searched or have been covered by spring rains. The strewn field map for the Houston event was less precise because the rock airburst at 29 miles up over a dense urban area, scattering fragments across a wide and largely unsearchable zone. Most of the Houston fragments are presumed to have fallen in residential yards, on rooftops, or in places where they are unlikely to be found unless they hit something noticeable. The Sherry James fragment is, so far, the only confirmed recovery from the Houston event. Others may exist, sitting unidentified in someone's gutter or backyard, mistaken for ordinary rocks. The Society maintains a list of preferred laboratories where suspected meteorites can be sent for analysis. The classification process is straightforward for experts. A few hours of testing can determine whether a stone is a genuine meteorite, what family it belongs to, and how it relates to other known falls. Anyone who suspects they have found a meteorite is encouraged to contact a regional astronomy club or university geology department for guidance. The hunt in the Ohio cornfields will continue for months. The hunt in the Houston suburbs may continue for years, with fragments occasionally surfacing as homeowners notice unusual stones in their yards. And the broader question of why so many fragments are arriving in the first place will continue to occupy researchers well beyond the spring of 2026. Most fireballs happen at night. The reason is simple. A streak of glowing rock against a black sky is dramatic and obvious. A streak of glowing rock against a sunlit sky has to compete with the sun itself for attention, and almost always loses. The vast majority of meteor activity in any given year goes entirely unwitnessed during daytime hours, because the rocks are not bright enough to outshine the surrounding daylight. To produce a true daytime fireball, the entering rock has to be unusually large or unusually fast, or both. The energy released by atmospheric heating has to be intense enough to generate a light source brighter than the sun, at least for a brief moment as the rock passes overhead. This is rare. The Society logs roughly 1 or 2 confirmed daytime bolides over the United States in a typical year, sometimes fewer. The first quarter of 2026 produced multiple confirmed daytime bolides. The European event on March 8 was a daytime bolide, watched by more than 3,000 people across 5 countries during the morning rush. The Ohio bolide on March 17th was a daytime bolide, exploding above Lake Erie at nearly 9 in the morning. The Houston bolide on March 21st was a late afternoon event in clear daylight conditions. That 3 confirmed major daytime bolides occurred within 13 days is, by itself, an anomaly. The historical rate for daytime bolides of comparable size suggests a baseline of perhaps 1 every several months, not 3 in 2 weeks. The clustering of large daytime events is one of the strongest indicators that the underlying population of incoming rocks has shifted, because the size threshold for daytime visibility is so high. The physics of daytime visibility makes the size estimate even more compelling. A nighttime fireball can be witnessed by thousands of people if it crosses a clear dark sky over a populated area. A daytime fireball requires the rock to be physically large enough to outshine the sun. The smallest rocks that can do this are typically in the multi-ton range. The Ohio rock at 7 tons was easily large enough to qualify. The Houston rock at 1 ton was at the lower end of the daytime threshold, which is consistent with reports that the event was bright, but not overwhelmingly so. The European bolide produced a slow, sustained brightness, consistent with a slow, shallow angle entry of a substantial rock. The shallow entry angle of the European event deserves special mention. Most fireballs come in at relatively steep angles, plunging through the atmosphere in seconds. A shallow angle means the rock skims the upper atmosphere on a long horizontal path, taking many seconds to traverse the sky. This produces a longer duration fireball and gives the event more visibility per observer. The European bolide held bright illumination for 5.5 seconds, more than twice the average duration of a typical fireball. There is a deeper concern hidden inside the daytime statistics. Daytime bolides are the rocks that telescope networks are least likely to detect in advance. Optical telescopes cannot see incoming objects against the bright background of the daytime sky. Radar detection can pick up some incoming rocks, but radar coverage of the inner solar system is patchy, and most small bodies are too small to register clearly. The asteroid surveys that scan the night sky for potentially hazardous objects mostly look in the direction away from the sun. A rock approaching from the direction of the sun is, in practical terms, invisible until it enters the atmosphere. This is the same blind spot that allowed the Chelyabinsk event in Russia in 2013 to surprise the world. That rock came in from the direction of the sun, exploding in the morning sky above the city with no advance warning from any detection network. It injured roughly 1,500 people, mostly from broken glass caused by the airburst pressure wave. The Chelyabinsk parallel is uncomfortable when applied to the 2026 surge. The daytime events of March came without warning. None of them were detected by any telescope or radar system in advance. They were observed only after they had already entered the atmosphere. If a larger rock arrived from a similar direction during this elevated period, the world would have no advance notice. The detection systems are simply not configured to see them. This is the part of the story that researchers tend to discuss in cautious language. The absolute risk in any given year remains small. The probability of a Chelyabinsk-scale event is low. The probability of a Tunguska-scale event is much lower. But the elevated rate of activity does shift these probabilities upward, and the daytime blind spot makes any individual event less detectable in advance than it would otherwise be. The catalogue that allows researchers to track these patterns is itself a remarkable piece of infrastructure, and its history involves data that was classified for decades. When a fireball appears in the upper atmosphere, the sensors that watch for it produce a specific kind of record. They produce a brightness curve. The curve shows how the fireball's light intensity changes over the seconds of its visible flight. This brightness curve, called a light curve in the technical literature, contains an enormous amount of information about the parent rock. The peak brightness of the light curve tells researchers the maximum energy release of the event. The duration tells them the entry angle and the deceleration profile of the rock. The shape of the curve, whether it rises smoothly to a peak and then fades, or shows multiple sharp peaks, tells them how the rock fragmented during entry. A clean single peak suggests a coherent rock that vaporized in one large event. Multiple peaks suggest staged fragmentation, with the rock breaking apart in pieces over the course of several seconds. By analyzing the light curve mathematically, researchers can estimate the kinetic energy of the original rock with reasonable precision. Kinetic energy depends on mass and velocity, and the relationship between energy and light output during atmospheric heating has been calibrated over decades of observation. The output of the calculation is typically expressed in kilotons of dynamite equivalent. For the Ohio event, the calculation came out to 250 tons. For the Houston event, 26 tons. For the European event of March 8th, similar but slightly higher numbers. These energy estimates are critical for understanding the size distribution of the incoming rocks. They are the numbers that go into the CNEOS catalogue. They are the numbers that researchers use to compare the 2026 surge against the historical baseline. They are the numbers that come back from infrasound networks and confirm the consistency of the measurements across multiple instruments. The light curve technique has been refined over decades of observation, but it is not perfect. The energy estimate depends on assumptions about the composition of the rock, its shape, and the atmospheric conditions at the time of entry. A stony asteroid will produce a different light curve than a metallic asteroid for the same kinetic energy. A high-angle entry produces a sharper curve than a shallow entry. The estimates carry uncertainty bars of roughly 30% in either direction. For the 2026 surge, the uncertainty bars matter less than the overall pattern. Even with 30% uncertainty on each individual event, the cumulative pattern of elevated activity is well outside the historical range. The signal is robust against measurement error. There is one other thing the light curve tells researchers that is increasingly important. It tells them the entry velocity of the rock. The entry velocity is critical for backtracing the orbit. A slow entering rock is on a relatively low energy orbit that does not extend far from the inner solar system. A fast entering rock may be on a long period orbit that takes it deep into the asteroid belt or beyond. The Ohio rock at 40,000 miles per hour was in the moderate range, consistent with an orbit between Mars and Jupiter. The European bolide at slightly higher speeds was in a similar range. The Houston event was at the lower end of the velocity range, consistent with a relatively nearby source. When researchers combine the entry velocity with the entry angle, they get a vector that can be projected backward through the gravitational field of the Sun to estimate the rock's prior orbit. This is the backtracing work that researchers are running on the 2026 events. The early results, as discussed in earlier chapters, point toward the Vesta family and the inner asteroid belt. More refined analysis is ongoing. The light curve technique is one of the unsung tools of modern asteroid science. It is the technique that transforms a brief flash of light into a measurable estimate of energy, orbit, and composition. Without it, the catalogues that anchor the 2026 analysis would not exist. And those catalogues took years to build, with platforms reaching the maturity required to support the kind of analysis researchers are doing now. The Society's Fireball reporting platform reached maturity around 2018. Before that, the system was less consistent. Some years had robust report counts. Other years had gaps in coverage. The system was upgraded several times, including major revisions in 2016 that standardized the way reports were filed and validated. This matters because any analysis of long-term trends has to account for changes in the data-gathering apparatus itself. If the platform was less effective in 2012 than in 2024, then comparing those 2 years directly would be misleading. You would see an apparent increase in fireballs that was really an increase in reporting capability. The Society's analysts addressed this by restricting their comparison to the 2018 through 2025 window, the period during which the platform had been continuously stable. Within that window, the annual numbers fluctuate normally but stay within a defined range. The 2026 numbers sit well outside that range. This is what gives the analysis its statistical power. By using only the post-2018 baseline, the researchers eliminate the question of whether the platform itself is producing more reports. The platform's behavior in 2026 is identical to its behavior in 2023 or 2024. What is different is the world it is reporting on. There are several other independent data sources that confirm the same pattern. The CNEOS catalog, operated by NASA's Jet Propulsion Laboratory, shows elevated energy events in early 2026. The infrasound networks operated by international monitoring organizations show elevated pressure wave signatures. The recovered meteorites themselves are physical evidence that cannot be faked or inflated by reporting bias. The convergence of multiple independent data sources on the same conclusion is what gives researchers confidence that the signal is real. If only the Society's eyewitness reports showed an anomaly, skeptics could argue that social media or smartphone adoption was inflating the numbers. If only the CNEOS catalog showed an anomaly, skeptics could argue that improved detection sensitivity was responsible. The fact that all three sources working from completely different instrumentation show the same elevated pattern means that the underlying physical event is real. The recovered meteorites add a final layer of confidence. A meteorite is an undeniable physical object. It exists in a laboratory. It has a mass, a chemistry, and a documented chain of custody, from the field to the analyzer. The German diogenite and the Ohio eucrite are real stones that arrived during the early 2026 surge. No amount of statistical argument can make those stones disappear. What the data cannot yet tell researchers is the precise size of the anomaly. The 3.9 standard deviation figure is a best estimate from independent analysts who pulled the CNEOS records and ran the calculation. The figure has not yet been formally validated by NASA. No peer-reviewed study has confirmed it. The figure is preliminary and may shift as more rigorous analysis is published in the coming months. But the direction of the signal is not in dispute. The numbers are elevated, the rocks are real, the pattern is global. The cause is unknown. Researchers are continuing to refine their analyses, and several teams are working on follow-up papers that will be published in the months ahead. The next critical data point will be the spring of 2027. If the elevated activity persists or grows, the surge is likely a multi-year phenomenon. If activity returns to baseline, the surge was a one-time wave. Either outcome will reshape how scientists understand the small body population near Earth. Either outcome will inform the modeling work and the policy discussions that follow. The geographic spread of the surge offers one more important piece of information about what is happening. The fireballs of early 2026 did not concentrate in one region. They spread across the entire daylit and nighttime portions of the globe in a pattern consistent with a uniform shift in the incoming rock population. North America logged events from Vancouver in the northwest to Houston in the south, from California in the west to Ohio in the east. Reports came from at least 16 states during the Ohio event alone. The Houston event was witnessed across Texas and into Louisiana. The California events on March 23rd produced reports from across the western state. Europe logged events across France, Germany, Switzerland, Belgium, the Netherlands, and Spain. The March 8th bolide alone drew reports from 5 countries. The March 11th event over France and Spain extended the European footprint. Smaller events throughout the month touched several other European nations. Asia logged confirmed events as well. Reports from observers in parts of Asia recorded bright fireballs during the same period, along with sonic boom detections from infrasound stations. The Japanese fireball in late 2025, which had been notable on its own, now appears in retrospect as a possible early indicator of the broader pattern that emerged the following spring. The geographic spread is important because it rules out any source that would produce a localized effect. A single fragmenting parent body would scatter material across a limited region. A localized atmospheric anomaly would only affect one part of the world. A geographic concentration would suggest a specific orbital geometry intersecting Earth in one particular zone. The actual data shows the opposite. The events spread across longitudes evenly. They spread across latitudes from the Canadian border to southern Texas. They appeared in both the morning and afternoon, in winter and early spring, on weekdays and weekends. Whatever is producing the surge is hitting the entire planet uniformly. This kind of uniform global pattern is exactly what you would expect from a population shift in the inner solar system. If more rocks are crossing Earth's orbit, Earth's rotation would expose every part of its surface to those rocks at some point. Over a quarter-year window, the rotation would average out any directional preference and produce a roughly uniform geographic distribution. The uniformity also makes the alien hypothesis harder to sustain. An artificial source would need to deploy its objects across the entire global atmosphere on a roughly uniform schedule. The complexity required would be substantial. A natural source, by contrast, only needs to be slightly elevated in its inner solar system flux to produce the observed pattern. Earth's rotation does the rest of the work. There is one more pattern worth noting in the geographic data. The events did not avoid populated areas. Several of them occurred over major cities or densely populated regions. The Ohio event was above a populated state. The Houston event was directly over a metropolitan area. The European bolide passed over multiple capital cities. This is partly a function of where people happen to live, but it is also a reminder that the rocks themselves do not target anything. They follow physics. They fragment where the atmospheric pressure dictates. Their fragments fall where gravity and wind direct them. This is what the Society means when it says the events were not coordinated. They are not coordinated. They are following ordinary ballistic trajectories that happen by the geometry of Earth's surface and the population distribution to bring them over populated areas in some cases. The randomness is also the reason researchers cannot predict where the next event will occur. The arrival of a major fireball is, in any practical sense, unpredictable. The detection systems are not capable of seeing most of these rocks before they enter the atmosphere. The most that can be said is that during periods of elevated activity, like the spring of 2026, the probability of an event in any given month is higher than during quiet periods. The Tunguska comparison, mentioned earlier, takes on additional weight in this context. The Tunguska event of June 1900 remains the largest confirmed airburst in modern history, a small asteroid or comet fragment, estimated at roughly 60 to 200 feet across, entered the atmosphere over a remote part of Siberia and exploded about 5 miles above the surface. The energy released has been estimated between 3 and 15 megatons of dynamite equivalent. The Tunguska blast flattened roughly 800 square miles of forest. Trees were knocked down in a radial pattern pointing outward from the blast center for 50 miles in every direction. Eyewitness reports from the few people in the region described a pillar of fire taller than the surrounding mountains, a roar that rattled houses 200 miles away, and a glowing night sky that lasted for several days across northern Europe. The reason Tunguska did not become a catastrophe is geography. The blast occurred over a remote area of Siberian forest, far from any cities or significant human population. The few people who witnessed it directly were nomadic herders and hunters, some of whom were knocked off their feet by the pressure wave. There were a small number of injuries, but no confirmed deaths. The forest absorbed the energy of the blast, and the surrounding wilderness absorbed the broader implications. If the same event had occurred over a major city, the consequences would have been catastrophic. The blast radius of a 15 megaton airburst at 5 miles altitude would have destroyed everything within tens of miles. Casualties would have numbered in the hundreds of thousands or more. The event would have been one of the largest single disaster losses of life in human history. This is the implicit benchmark that scientists use when discussing the broader risk from large incoming rocks. The Ohio bolide at 250 tons of dynamite equivalent was about 1/10,000th the energy of the smaller end of the Tunguska estimate. The Houston event at 26 tons was about 100,000th the energy. These are tiny events on the Tunguska scale. The probability of a Tunguska scale event in any given year remains very low. The historical rate is roughly one such event every few hundred to 1,000 years. Even an elevated period like 2026 does not significantly change this estimate, because the events in the current surge are several orders of magnitude smaller than Tunguska. What the elevated period does change is the probability distribution of smaller events. More large fireballs in any given year means more sonic booms, more meteorite falls, more potential damage from individual events even at the small scale. A meteorite through a roof is a localized event. A larger meteorite intact at the ground would be a more serious one. The Ohio event, if it had occurred at lower altitude or over a more populated area, might have produced significant damage from its pressure wave. The Chelyabinsk event of 2013 is the closer parallel in scale. That rock entered the atmosphere at roughly 20 meters across and exploded in the morning sky above the Russian city of Chelyabinsk. The airburst released energy equivalent to roughly 500 kilotons of dynamite, or about 2,000 times the Ohio energy. The pressure wave broke an enormous number of windows across the city and injured nearly 1,500 people, primarily from flying glass. No one was killed by the rock itself, but the disruption was significant. The Chelyabinsk rock was not detected before entry, the Ohio rock was not detected before entry, none of the 2026 rocks were detected. The detection systems are simply not built to catch objects in the size range that these events represent. This is the policy question that the surge raises. Should detection systems be expanded to catch smaller rocks, the cost would be substantial, and the warning time even for detected objects would often be too short to take any meaningful protective action. But the alternative is what we have now, which is a complete blind spot for everything below the size of a roughly 100-meter asteroid. The argument for expanded detection is partly statistical. If the population of small Earth-crossing rocks is larger than previously estimated, the probability of a damaging event in any given year is higher than current models suggest. The 2026 surge is contributing data that, if confirmed in subsequent years, would shift the risk estimates upward. The known population of asteroids and meteoroids is itself smaller than the actual population. NASA and several other agencies maintain catalogues of known asteroids and meteoroids in Earth-crossing orbits. The largest objects, those with diameters of roughly half a mile or more, are nearly fully catalogued. NASA estimates that more than 90% of these large near-Earth objects have been discovered and are being tracked. The risk from any large unknown rock is therefore relatively low. We would see one coming, in most cases, years or decades in advance. The smaller objects are a different story. The catalogue of asteroids with diameters between 60 feet and a few hundred feet is far less complete. Estimates suggest that fewer than half of these objects have been discovered. The catalogue of smaller objects, down to the size of the rocks involved in the 2026 surge, is largely empty. We have detected only a small fraction of the rocks in this size range that exist in Earth-crossing orbits. This is what astronomers call the small end gap. The big rocks we know about. The medium rocks we mostly know about. The small rocks are a vast, hidden population. And the rocks in the surge are at the upper end of this hidden population, in the size range where detection is technically possible, but where the survey infrastructure has not yet caught up. The reason for the gap is mostly practical. Telescopes capable of detecting small asteroids must scan the night sky systematically, recording every faint moving object and tracking it long enough to determine its orbit. The work is time-consuming and expensive. The major asteroid surveys like the Catalina Sky Survey and the Pan-STARRS network have prioritized larger objects because they pose greater individual risk. The smaller rocks have received less attention. A new generation of survey instruments is changing this. The Vera Rubin Observatory in Chile is expected to dramatically increase the rate at which small near-Earth objects are detected. The NEO Surveyor mission, an infrared telescope planned for launch later this decade, will detect objects that are invisible to ground-based optical surveys. These new tools will eventually narrow the small end gap. But for now, the gap is real. The rocks falling in 2026 are from a population that is mostly uncatalogued. We do not know where they were a year ago. We do not know where the rest of their orbital family is. We do not know how many similar rocks are still out there. This is the most uncertain part of the broader story. The 2026 surge involves rocks that fall into a detection gap. The elevated rate, if it continues, would imply that the population is larger than current estimates suggest. Or it would imply that the population is undergoing a temporary disturbance that has scattered more rocks into Earth-crossing orbits than usual. Both possibilities have implications for the risk estimates. A larger underlying population means more events per year on average. A temporary disturbance means a finite period of elevated risk followed by a return to baseline. The data does not yet distinguish between these two possibilities. What it does distinguish is the immediate question of what to expect in the coming months. If the disturbance is recent and concentrated, the elevated activity will fade as the wave passes. If the disturbance is broader, the elevated activity will persist or grow. The spring of 2027 is the next critical observation window. There is one more uncomfortable detail in the detection picture. Even the largest planned surveys are optimized for nighttime detection of objects approaching from the direction away from the Sun. Objects approaching from the direction of the Sun, like the Chelyabinsk rock, and several of the daytime bolides of 2026 are essentially invisible to optical surveys until they enter the atmosphere. This is the daytime blind spot. A rock approaching from the direction of the sun would not be detected even by a fully operational future survey unless it was very large. Smaller rocks, in the size range of the 2026 fireballs, would arrive without warning. The detection infrastructure is improving, but the blind spot remains. The reason the daytime blind spot exists is fundamental. Optical telescopes work by detecting reflected sunlight. A rock approaching from the direction of the sun is illuminated on the side facing away from us. The side facing Earth is in shadow. Such an object reflects almost no light toward us, and the bright background of the sun's glare makes it nearly impossible to pick out, even if it did reflect light. This is not a problem that can be solved by building better optical telescopes on Earth. The physics of the geometry is unavoidable. The sun is too bright. The Earth-facing side of an incoming rock is too dark. The combination produces a blind zone that no ground-based optical survey can ever cover. There are partial solutions. Space-based infrared telescopes can detect the heat signature of small asteroids, regardless of their angle relative to the sun. The planned NEO-Surveyor mission is specifically designed to address this problem. An infrared telescope, in space, can see warm objects against the cold background of deep space, and it can do so even for objects approaching from the direction of the sun. The NEO-Surveyor will not be operational for several more years, however. In the meantime, the blind spot is real. Roughly half of the inner solar system, in terms of approach direction, is essentially invisible to current detection systems. The Chelyabinsk event of 2013 demonstrated this concretely. The rock approached Earth from the direction of the sun in the morning sky. No telescope detected it before entry. It exploded above a Russian city of more than 1 million people, broke windows across the metro area, and injured nearly 1,500 people. The event happened without any advance warning. The 2026 daytime bolides over Ohio and Europe were similarly undetected. They arrived without warning. They were observed only after entry. If a larger rock arrived from the same direction during this elevated period, the situation would be effectively the same. The world would have no notice. This is the policy reality that researchers and planners are working with. The detection infrastructure is improving, but it cannot fully solve the daytime problem until space-based infrared surveys are operational. The 2026 surge is happening within this gap. The good news is that the rocks falling in the surge are still in the size range that produces local rather than global damage. A Tunguska-scale event remains very unlikely in any given year. The events that are happening now produce sonic booms, rare roof strikes, and the kind of localized damage that is alarming but not catastrophic. The harder news is that the population that we cannot see also includes rocks in size ranges above the current surge. The full distribution of small Earth-crossing objects extends from the pebble scale up through the kilometer scale. Most of the smaller objects are undetected. Some fraction of those objects will eventually enter the atmosphere. The probability of any one of them being on a damaging trajectory in any given year is small, but the population of risk is not zero. The Society's analysis of the 2026 surge does not address policy questions directly. Their job is to document the pattern and characterize the underlying physical event. The policy implications, like decisions about funding for detection infrastructure, are the work of NASA, the European Space Agency, and the governmental bodies that fund these agencies. The pattern they are documenting suggests that the question deserves attention. The surge is happening, the rocks are real, the detection infrastructure is not yet adequate to catch most of them in advance. These facts do not produce immediate alarm, but they do produce a sense that the work of building better detection is more urgent than the absolute current risk would suggest. What happens next will determine how this story is remembered. The spring of 2027 is the next critical observation window. If the elevated activity of 2026 was a temporary wave, the rate should return to baseline by then. If it was the leading edge of a longer-term pattern, the elevation should persist or grow. Several research groups are already preparing for this observation window. The Society will continue to log fireball reports through its standard platform. NASA's CNEOS catalog will continue to receive bolide data from infrasound and satellite sensors. The European Space Agency will continue to track recovered meteorites and analyze their chemistry. Independent analysts will continue to pull the data and run statistical comparisons. The most important piece of new science will come from the orbital backtracing work that is underway now. If researchers can identify a common source region in the asteroid belt for the recovered fragments of 2026, the source identification will be a major contribution to the understanding of asteroid family dynamics. A recent collision among Vesta family members, scattering fresh debris inward, would be the kind of event that has been theorized for decades, but never observed directly. The follow-up analyses of the recovered meteorites will also be important. The German diogenite and the Ohio eucrite are now being studied with the full range of modern analytical techniques. The cosmic ray exposure ages of these rocks will tell researchers how long they have been wandering in space as small fragments. If the exposure ages cluster around a similar number, it would support the hypothesis of a recent collisional event that scattered new fragments together. If the ages are widely scattered, it would suggest a longer-term background increase rather than a single recent event. The detection infrastructure will continue to improve. The Vera Rubin Observatory is now operational and is expected to dramatically increase the discovery rate of small near-Earth objects over the coming years. The NEO-Surveyor mission is in development. Ground-based radar systems are being upgraded. The catalogue of known Earth-crossing rocks will expand significantly in the next decade. If the 2026 surge persists into the coming years, the implications would extend beyond pure science. Insurance models would need to be updated. Building codes for unusual events might be reconsidered. The probability of an individual roof strike, while still very low, would shift upward enough to matter at the aggregate scale. Population centers might want to consider how their building stock would respond to a Chelyabinsk-scale event. These are quiet considerations rather than urgent alarms. The absolute risk in any given year remains small. The events that are happening now are localized in their effects. The Tunguska or larger-scale event remains a rare long-term concern rather than a near-term threat. But the small rocks that are arriving in elevated numbers do produce real effects on real people, and the elevated rate increases the frequency of those effects. For the researchers most directly involved, the work is exciting in a way that may be hard to communicate to people outside the field. The chance to observe a wave of debris arriving in real time, to recover meteorites within hours of their fall, to backtrace orbital histories with new tools, is the kind of opportunity that comes rarely in a career. The science of small bodies in the inner solar system is being rewritten in front of them. For everyone else, the story is simpler. The sky has been louder than usual this year. The rocks have been bigger. The bolides have been brighter. The meteorite hunters have been busier. The researchers have been more concerned than they normally are. Whether the rate stays elevated, returns to baseline, or grows further is the question that will define the next chapter of this story. The data needed to answer that question is being collected right now, every night and every day, on every continent. The sky has been telling us something. The signal is real. The cause is not yet known. The work to find out is underway, and the answer, when it comes, may reshape how we understand the small bodies of the inner solar system. What we know is that something has changed. What we do not yet know is whether it is changing back. That answer is coming. We just have to keep watching.